The shadow beyond Neptune. For decades, humanity believed it had mapped the solar system with confidence. From the blazing surface of Mercury to the icy winds of Neptune, the story felt complete, neat, symmetrical, and final. Pluto's demotion in 2006 was supposed to be the last great planetary controversy. The textbooks were rewritten, diagrams simplified, and the solar system was declared understood. But the universe has a habit of humbling certainty. Quietly, far beyond the orbit of Neptune, something began to misbehave. Objects at the edge of the solar system, small, frozen worlds drifting in darkness, were not moving the way gravity said they should. Their paths were twisted, clustered, aligned in ways that defied randomness. It was as if an unseen hand was shaping their motion from the shadows. And slowly, reluctantly, astronomers began to whisper a dangerous idea: maybe the solar system was not finished after all. The region where this mystery unfolds is the Kuiper Belt, a vast, dim halo of icy debris extending billions of kilometers beyond Neptune. It is a graveyard of ancient leftovers from the solar system's formation, a place where time moves slowly and sunlight is little more than a memory. For most of modern astronomy, the Kuiper Belt was treated as background noise, a collection of insignificant rocks and dwarf planets. But as telescopes grew more powerful and surveys more precise, patterns began to emerge. Certain Kuiper Belt objects, known as extreme trans-Neptunian objects, shared strangely similar orbits. They were tilted in the same direction, elongated in the same way, and clustered as if guided by an invisible gravitational shepherd. In a universe governed by chaos and probability, this kind of alignment should be nearly impossible. Yet the data kept repeating the same unsettling message: something massive was out there. At first, scientists resisted the implication. Astronomy is a discipline built on skepticism, and proposing an unseen planet is not done lightly. History carries scars, most famously the hypothetical planet Vulcan, once proposed to explain Mercury's orbit, only to vanish when Einstein's theory of relativity provided the real answer. No astronomer wanted to repeat that embarrassment, so alternative explanations were tested. Maybe observational bias was fooling researchers. Maybe the gravitational pull of many small objects combined to create the illusion of order. Maybe the models were wrong. But as years passed and more data poured in from observatories across the world, those explanations began to collapse under their own weight. The alignment was too precise. The clustering too consistent. The probability of chance too small to ignore. Then, in 2016, two astronomers from Caltech, Konstantin Batygin and Michael E. Brown, did something bold. They put a name to the ghost. In a paper that would ripple through the scientific world, they proposed the existence of a ninth planet, massive, distant, and unseen. According to their calculations, this object could be 5 to 10 times the mass of Earth, orbiting the Sun at a distance so vast that a single year there would last thousands of Earth years. Its path would be highly elliptical, carrying it deep into the darkness beyond Neptune before swinging slowly back inward. This planet, they argued, could explain everything: the tilted orbits, the clustering, even the strange angles of distant objects that seemed to defy the solar system's flat plane. They called it, cautiously, Planet 9. The reaction was immediate and electric. Headlines exploded across the world. A new planet discovered, Planet 9 lurking in the dark. The solar system's hidden giant. For the public, it felt like a return to childhood wonder, the idea that a massive world could be hiding just beyond our cosmic doorstep. But within the scientific community, excitement was tempered by caution. Planet 9 had not been seen. No telescope had captured its light. No spacecraft had detected its presence directly. Everything rested on mathematics, on gravitational fingerprints left behind like cosmic footprints in the snow. And in science, evidence inferred is never as powerful as evidence observed. Still, the case for Planet 9 grew stronger with time. Independent teams began reanalyzing the data. New Kuiper Belt objects were discovered, and instead of weakening the hypothesis, they reinforced it. The orbits kept lining up. Simulations showed that without a massive distant planet, the observed configuration should unravel over millions of years. Yet it remained stable, as if anchored by something real. Even more intriguing, Planet 9 could explain why some objects orbit the Sun backwards, against the general flow of the solar system. Such retrograde orbits are rare and difficult to produce. But introduce a distant giant planet, and suddenly the math works. Yet mystery layered upon mystery. If Planet 9 exists, where did it come from? One possibility is deeply unsettling. It may not have formed where it now resides. Early in the solar system's violent youth, giant planets migrated, collided, and scattered debris like shrapnel. Planet 9 could be a survivor of that chaos, either flung outward by Jupiter and Saturn or captured from another star during a close stellar encounter when the Sun was young. This would mean our solar system is not the orderly family portrait we imagine, but a relic of cosmic violence, shaped by near misses and gravitational theft. The hunt intensified. Powerful telescopes were turned toward the sky. The Subaru telescope in Hawaii, the Dark Energy Survey in Chile, and others scanning vast stretches of space night after night. But Planet 9 is a master of concealment. At such extreme distances, even a planet larger than Earth would reflect almost no sunlight. It would move slowly, so slowly that distinguishing it from background stars becomes a monumental challenge. Months of observation might reveal nothing more than a faint dot, barely shifting against the cosmic backdrop. Finding Planet 9 is not like spotting Mars or Jupiter. It is more like searching for a grain of coal drifting through a black ocean the size of the solar system itself. And then came the doubt. As the years passed without direct detection, critics grew louder. Some argued that the data set was still too small, that hidden biases in observation could still be fooling researchers. Others proposed radical alternatives. Perhaps the Kuiper Belt itself has mass we don't fully understand, or perhaps our models of gravity begin to break down at extreme distances. A few even suggested that Planet 9 might not be a planet at all, but something far stranger, an ancient black hole, a primordial relic from the early universe passing silently through our solar system. The idea sounds like science fiction, yet it highlights just how deep the mystery runs. What makes the hunt for Planet 9 so powerful is not just the possibility of a new world, but what it represents. It is a reminder that even in our own cosmic backyard, enormous secrets can remain hidden. That the maps we trust may still have blank spaces. That certainty in science is always provisional, waiting to be challenged by new evidence lurking just beyond the reach of our instruments. Planet 9, real or not, has already changed astronomy. It has forced scientists to look outward again, to question assumptions, to admit that the solar system may still be incomplete. And this is only the beginning of the story. Because as technology improves, as new telescopes come online, and as surveys grow deeper and wider, the darkness beyond Neptune is finally being peeled back. The question is no longer, could Planet 9 exist? The question now is far more unsettling. If it exists, how close are we to finally seeing it? Chasing a ghost in the darkness. By the time Planet 9 became a serious scientific contender, the hunt was no longer theoretical, it was operational. This was no longer about equations on whiteboards or simulations running quietly on university servers. Telescopes across the planet were being tasked with one of the most difficult searches in modern astronomy, finding a cold, slow-moving world hiding in the most distant reaches of the Sun's gravitational dominion. Unlike planets closer to the Sun, Planet 9 would not blaze across the sky. It would barely crawl. Night after night, astronomers stared at the same fields of stars, comparing images taken weeks or even months apart, hoping to catch the faintest whisper of motion. The challenge was not just technical, it was philosophical. They were searching for something that, by its very nature, did not want to be found. The primary weapon in this hunt was data, vast, overwhelming quantities of it. Modern sky surveys capture millions of celestial objects in a single sweep, producing catalogs so large that no human could ever examine them manually. Algorithms became the new explorers, sifting through oceans of starlight in search of anomalies. Yet Planet 9 was different. Most search algorithms are designed to detect fast-moving objects like near-Earth asteroids or bright transients like supernovae. Planet 9, if it exists, would move so slowly that it could masquerade as a star for years before revealing itself. This forced astronomers to rethink how they search the sky, developing new methods to detect motion at the edge of perceptibility. One of the most critical tools in this pursuit was the Subaru telescope atop Mauna Kea in Hawaii. With its massive mirror and wide-field camera, Subaru was uniquely suited to scan large portions of the sky with extreme sensitivity. Michael Brown and his collaborators devoted hundreds of hours of observation time to this single objective, carefully targeting regions of space where Planet 9 was statistically most likely to be hiding. These regions were not chosen at random. They were guided by the gravitational fingerprints left behind in the Kuiper Belt, the clustered orbits that pointed like arrows toward the unseen planet's probable location. Each observation was a gamble. Each night ended with either hope or disappointment. And disappointment came often. Years passed. Fields were scanned. Candidates emerged, only to be ruled out after closer inspection. A distant galaxy masquerading as a point of light. A faint star with unusual color. A moving object that turned out to be something far closer and far smaller than hoped. To the outside world, the silence was interpreted as failure. Headlines quietly faded. The idea of Planet 9 began to feel like a ghost story, thrilling, but possibly imaginary. But within the scientific community, something more subtle was happening. The absence of detection was not killing the hypothesis. It was refining it. Every failed search narrowed the possibilities. Planet 9's orbit became more constrained, its potential brightness more precisely estimated, its position in the sky more sharply defined. Like a sculptor removing stone to reveal a form, astronomers were carving away uncertainty. At the same time, new discoveries continued to strengthen the original anomaly. More extreme trans-Neptunian objects were found, and their orbits continued to show the same eerie alignment. Even when accounting for observational bias, the pattern refused to vanish. The solar system was still whispering the same secret. Then came an unexpected twist. Some simulations began to suggest that Planet 9's influence might be even more profound than originally thought. Not only could it explain the clustering of distant objects, but it could also account for the slight tilt of the entire solar system itself. The plane in which most planets orbit the Sun is tilted relative to the Sun's equator, a subtle but puzzling fact. Introduce a massive, distant planet pulling gently over billions of years, and suddenly the tilt makes sense. Planet 9 was no longer just an explanation for odd debris at the edge of the solar system, it was becoming the central architect of its structure. Yet skepticism remained healthy and fierce. Some researchers proposed an alternative that was equally dramatic. What if the clustering of Kuiper Belt objects was the result of collective gravity? Instead of one large planet, perhaps thousands of smaller icy bodies, acting together, could produce the same effect. This idea gained traction briefly, offering a way to explain the data without invoking an unseen giant. But detailed modeling revealed a fatal flaw. The Kuiper Belt simply did not contain enough mass. To reproduce the observed orbits, it would need to be far heavier than observations allowed. The numbers refused to cooperate. Another hypothesis pushed even further into the unknown. Some physicists wondered whether our understanding of gravity itself might be incomplete at extreme distances. Modified gravity theories, often discussed in the context of galaxies and dark matter, were cautiously invoked. Could the Sun's gravitational influence behave differently tens of billions of kilometers away? It was an enticing idea, but one with enormous implications. Accepting it would not just rewrite the solar system, it would rewrite physics. And once again, the evidence failed to support such a radical shift. The simplest explanation, as uncomfortable as it was, continued to point back to Planet 9. As the 2020s unfolded, the search entered a new phase. A new generation of telescopes promised to change everything. The Vera C. Rubin Observatory, with its unprecedented ability to scan the entire sky repeatedly and deeply, was poised to become a game changer. Unlike previous surveys, it would not just look once, it would watch the sky evolve over time, building a dynamic map of motion across the cosmos. For an object like Planet 9, this was crucial. Slow movement would no longer be a weakness, it would be a signature. At the same time, astronomers began reanalyzing decades of archival data. Old images taken for entirely different purposes were revisited with fresh eyes and modern algorithms. Somewhere in those dusty digital archives, Planet 9 could already be hiding, captured unknowingly, waiting for someone to notice that it had shifted ever so slightly between exposures separated by years. The idea was tantalizing. The possibility that the planet had already been photographed, but not yet recognized. Still, uncertainty lingered like a shadow. Each year without detection raised the stakes. Was Planet 9 simply farther than expected? Darker, smaller, or was the solar system playing a trick on us, tempting scientists with patterns that dissolved just before certainty? The emotional toll on researchers was real. To spend years chasing a hypothesis that might collapse is the risk every scientist accepts, but few experience it so publicly. Every new paper, every conference presentation carried the unspoken tension between hope and doubt. And yet, the hunt did not slow. If anything, it became more focused, more determined. Because Planet 9 is not just about finding another dot in the sky. It is about understanding how solar systems form, how chaos settles into order, and how much of our cosmic neighborhood remains unexplored. Whether Planet 9 exists or not, the search itself is exposing the deep structure of the solar system in ways never imagined before. As telescopes sharpen their gaze and algorithms grow more sophisticated, the darkness beyond Neptune feels less empty than it once did. Something is shaping those distant orbits. Something is whispering through the gravity of frozen worlds. The only question left is whether that something will finally step into the light, or whether it will force science to confront an even stranger truth. Because if Planet 9 is not there, then what, exactly, has been guiding the solar system from the shadows? The answer waiting in the dark finally. For a mystery to endure this long, it must sit at the intersection of evidence and absence. Planet 9 exists precisely in that narrow space, where mathematics screams certainty, but the universe remains silent. By the mid-2020s, the hunt reached a critical moment. The question was no longer whether astronomers believed in Planet 9, but whether the tools of modern science were finally capable of exposing it. The launch of next-generation surveys marked the beginning of what many quietly called the endgame. Either Planet 9 would be found, or its ghost would finally be laid to rest. The Vera C. Rubin Observatory, designed to scan the entire visible sky every few nights with unmatched depth, fundamentally changed the rules of the search. For the first time, astronomers were no longer taking isolated snapshots of the universe, they were creating a time-lapse movie of the cosmos itself. Any object moving, no matter how slowly, would eventually betray its presence. If Planet 9 existed within the predicted range of distances and brightness, Rubin would see it. This fact introduced an uncomfortable clarity. The mystery now had a deadline. As early data began to arrive, anticipation surged. Researchers cross-checked predicted orbital zones with fresh observations, narrowing the hiding places to increasingly precise corridors of sky. The planet's possible mass, reflectivity, and temperature were re-evaluated again and again. If it was darker than expected, it could still escape detection. If it was farther, colder, or on a more inclined orbit, it could remain hidden just beyond the threshold. But each adjustment came at a cost. The more Planet 9 retreated into darkness, the more finely tuned it had to be. And finely tuned explanations make scientists uneasy. At the same time, something remarkable happened. The behavior of distant Kuiper Belt objects continued to evolve as new members of that population were discovered. While the original clustering remained suggestive, it became slightly less perfect. Not broken, just softened. Some objects deviated from the original alignment. Others introduced new complexities that did not fit cleanly into early models. This did not disprove Planet 9, but it reopened the door to alternative interpretations. The universe was reminding scientists of an uncomfortable truth: patterns can shift as knowledge grows. One alternative explanation gained renewed attention, not as a replacement, but as a competitor. Could the early solar system itself, chaotic and violent, have produced these orbital alignments without the need for an extra planet? Massive interactions between Jupiter, Saturn, and the primordial disk of debris could have sculpted long-lasting structures that persist to this day. In this view, the Kuiper Belt is not being guided by a present-day shepherd, but haunted by its past. The gravity is no longer there, but its imprint remains. Then came the most radical possibility of all, that Planet 9 once existed, but no longer does. In the early solar system, planets were not guaranteed survival. Many were ejected into interstellar space during gravitational battles. If a massive planet had once orbited the Sun and was later thrown outward, it could have shaped the Kuiper Belt before disappearing forever. The alignments we see today would be a fossil, evidence of a world that no longer belongs to us. A planet that once was, but now drifts between the stars. This idea is both elegant and tragic. It resolves the mathematical evidence while explaining the silence of modern telescopes. But it also robs humanity of the dramatic discovery it longs for. No new world to name. No distant sunrises to imagine. Only the quiet realization that the solar system has already lost something it never knew it had. And yet, even this possibility is not the end of the story. Because whether Planet 9 exists now, existed once, or never existed at all, the hunt has already changed science. It has expanded our understanding of the solar system's edge, revealing it not as a static boundary, but as a dynamic, evolving frontier. It has shown that gravity's reach is subtle, patient, and capable of shaping worlds across billions of kilometers and billions of years. Most importantly, it has reminded humanity that knowledge advances not just through answers, but through the courage to ask uncomfortable questions. So, is the hunt for Planet 9 finally over? The most honest answer is this: we are closer than ever, but certainty still waits in the dark. If Planet 9 is there, it will not remain hidden forever. The sky is being watched with unprecedented precision. The shadows are shrinking, and the universe, eventually, always reveals its secrets. But if Planet 9 is not there, if the final surveys come back empty, then the discovery will be just as profound. It will mean that the solar system is stranger than we imagined, capable of preserving echoes of long-lost events in the silent orbits of frozen worlds. It will mean that absence itself can be evidence. And it will mean that even without finding a new planet, we have uncovered a deeper truth about how cosmic systems remember their past. In the end, Planet 9 is not just a question about a distant world. It is a question about how much of reality lies beyond what we can see. About whether the universe owes us neat explanations, or demands patience instead. About whether discovery always means finding something new, or sometimes, learning why something is missing. The darkness beyond Neptune is no longer empty. It is filled with meaning. And whatever the final answer may be, one thing is now certain. The solar system is still full of surprises.